Hello, this lecture is called Linear Dependence and Spans. So we first review this theorem called dependency in linearly dependent sets. This is going to be referred as DL DS. And we first note that we have a set of vectors, set of column vectors. Well, it doesn't matter if they're column vectors or not, but we have a set of vectors here called S. And so this set contains, these are the elements of this set. There are n elements, n members of that set. And so we're going to come up, this theorem is providing a criterion to rule linear dependence. Okay. In fact, this is if and only if. That means that if okay, so you'll see how this works. So we have n vectors, and this is telling us that if there exists, if there is such an index, this index t, for any of these numbers between 1 and n, okay, if there is at least one index of one of these numbers between 1 and n, such that you can select that vector with that index out of the set S, and have the following be true, the rest of the vectors. So here's u1 through u sub, here's the first subset of partition, u1 through u sub t minus 1. And then here is the rest of the vectors from t plus 1, t plus 2, all the way through n, such that the rest of the vectors form a linear combination that is exactly equal to that one vector. So let's say, for example, that we have u1, u2, u3, and u4. So what this is referring to is like, let's select one index. Let's say there is such an index. For example, let's say that that index here is t equals 4, just for the sake of an example. And we say, if it is possible to write u4 as a linear combination of the other remaining vectors, okay, in this case u1, u2, u3, and u1, u2, and u3, if there are scalars, for example, alpha 1, alpha 2, and alpha 3, that make this linear combination be exactly equal to the vector with that index, then in that case we are invoking, this theorem provides the means, this means of ruling this as a linearly dependent set. Okay, so if at least if one of the vectors can be expressed as a linear combination of the rest of the vectors, that is a clear footprint, that's a clear sign of linear dependence. Okay, so let's see this in more detail. The other thing that we're going to make use of is this theorem here that says, suppose we have a set of vectors, and we're interested in the span of that set of vectors, and when we stack the vectors into a matrix, compute the RREF, we take a closer look at the indices on the set D, the indices that we consider indices. If this were about in the context of solving linear systems, this would be the indices for dependent variables. These are the indices for pivot columns, right? Well, those indices would provide a way of selecting a subset from the original set S, such that the vectors with those indices form a linearly independent set. Okay, so this is important because it's a way of selecting a subset that is linearly independent, and it also has the property that the span of this subset is exactly equal to the span of the original set, which is here called W. Okay, so this is a way of selecting a subset that is linearly independent and spanning, also known as a basis. So here we have an example. Let's say we're working with this the columns of this matrix. So when we say that we're considering a set here, we mean that T is going to be, as a set, is going to contain 4 members, right? And these 4 members are as a set. It's not the same as saying, if you say that T equals B, then this is not right, because B is a matrix and we're thinking about considering the columns of B, okay, as members of a set. So this is how we formulate, this is what we mean: -3, -1, 1, 1, 2, 1, -2, -2, 1, 2, and then 7, 4, and -1. So these are the columns as members of a set, and that's what we are considering here. T be the set of columns of this matrix. So the question is this set linearly dependent? Well, here we make use of RREF, form the matrix already formed, right? But row reduce, and from here we would conclude that the set is not linearly independent, is in fact linearly dependent. This is a direct implication of the reduced row echelon form. However, you know, in view of that, remember the theorem we previously quoted here, the theorem about linearly independent and spanning sets, and how to select such a set, the so-called basis of the span. We know here that the set with containing indices of pivot columns contains numbers or indices 1 and 2, which means that we can, this would be column 1, this would be column 2 right here. So we select those 2 vectors. That set, considering these 2 vectors as members of a set, this set would be linearly independent, or these 2 vectors are also linearly independent. So T has 4 members, and if we wanted to make use of the theorem, we can say, you know, we can actually find a vector that can be expressed as a linear combination of the linearly independent vectors. So that's the motivation here. So we say, you know, let's explore how can we make the vector, this vector T 7, 4, -1. Remember, this is one. This is one of the column vectors of this matrix. Can this vector be expressed as a linear combination of the 2 vectors that the theorem tells us are linearly independent? And so, in other words, we're asking this type of question, like, can this vector be expressed as a linear combination of the other 2? So here's the linear combination, and what we need to determine is what are the values of scalars that make this true. So this is the same type of question the same type of question we would address. You know, this scalar, let's say, is alpha 1, and this is alpha 2, and let's say that this vector is b1 and this vector is b2. So we could form a matrix with b1, b2, and 7, 4, and -1. This would be an augmented matrix, and then we would compute RREF. This is exactly the type of question. Finding those scalars is analogous, is equivalent to finding solutions of a system of linear equations, right? And so by row reducing, we would be able to find the solution set, and in this case, the unknowns are alpha 1 and alpha 2. This, right, tells you that we have 1 alpha 1 equals -2, and then the second row tells you that 1 alpha 2 equals 1, right? So it's possible to find such scalars that give a meaning to this linear combination. Those scalars are -2 and 1, and they make the linear combination to be 6, 2, -2 added to 1, 2, 1, and that indeed is 7, 4, -1.